Okay, guys, we're going to get started today. Please join me in welcoming Professor Stephen Kane, who is at the University of California, Riverside. Stephen grew up in the outback of Australia. True story. You should ask him about it. And he then graduated with his bachelor's from Macquarie University. I've been really stumbling on this pronunciation, so. He got his PhD from the University of Tasmania and went on to St. Andrews for his PhD, followed by the University of Florida. He was also at Nexi at Caltech and has done an enormous amount of work, especially finding habitable zone planets using SuperWASP, TESS, JWST, and Hubble. Dr. Kane's work has been featured in the BBC, CBS, National Geographic, Space.com, and many other venues. And most recently, he's been asked by not one, but two Discovery missions to Venus, that's Veritas and Da Vinci, to represent them in Congress for congressional visits this October. Please welcome Dr. Stephen Kane.
Thank you. Thanks for that great introduction. And thank you all so much for coming along. It's a real pleasure to be here. Thank you for inviting me out. And I'm going to be talking to you today about something which I've become very passionate about because my background is that I was very interested in planetary science. I actually intended on starting a PhD on Venus. This was in 1995. But at that same time, there were some interesting discoveries happening regarding the discovery of planets outside of our solar system, 51 Peg-B, and started a whole franchise where a project in exoplanets became viable for a mere graduate student such as myself. And so that's the direction that I went. However, in 2009, the Kepler mission was launched. And the focus of that mission was to find planets the size of Earth around other stars. And I kept saying to the Kepler mission folks, wait, that's the same as Venus, right? And they didn't want to hear that because it's a different narrative. And so at that point, I realized, well, we need to know more about Venus. I started going to Venus meetings, and I'll be talking about some of that during this talk. But long story short, I've become very interested in where the overlap are in these fields of planetary science and exoplanets, which is largely astrophysics. And I'm very excited to talk to you all about this because this is kind of a perfect demographics of people and scientific interests for this kind of a talk because we have representation here from astrophysics, planetary science, engineering, people who think about next generation space missions. So hopefully I'll be giving you some ideas about what the collaborative opportunities are. So to start out with, I'll just mention that some of the things I'll be talking about today were from a review paper that I published with my colleagues a few years back, where after the very first exoplanets in our backyard meeting, which was held in Houston in February of 2020. For many people, it was the last in-person meeting we had before the pandemic. And then we went home and we stayed there. But whilst I was trapped at home, I wrote this with the help of my colleagues and just really explored what these connections are between these fields. And so that's what I'll be talking to you about today. But I want to start out by talking about two important documents that I'm sure you're all familiar with. And that is the Astrophysics Decadal and the Planetary Science and Astrobiology Decadal. So the Astrophysics Decadal shown on left, Planetary Science Decadal shown on the right. And there's just a goldmine of interesting quotes to pull out of these decadals. But we're going to play a game of pick that decadal. I'm going to show you a quote, and I want you to guess with a raise of hands. Maybe it won't be a guess which decadal that came from. So the first one, the planets in our solar system and the sun at the center of it provide the most direct connection to the myriad of other stars and planets in our galaxy and the universe? Raise your hand if you think that came from the astrophysics decadal. A lot of hands. Who thinks it came from the planetary science decadal? It's about half and half. The answer is that came from the astrophysics decadal. Very interesting, right? Because it's a recognition from the exoplanet community of, hey, solar system is the foundation. It's where it all starts. One more quote. This one is, increased interactions between the astronomy and planetary science and astrobiology communities, supported under, for example, NASA's planetary science and astrophysics divisions, are needed to maximize advances in exoplanetary science. Raise your hand if you think that came from astrophysics. Fewer hands. And who thinks it came from planetary science? Well, if you thought I was trying to pull a fast one and give you 2 quotes from the astrophysics decadal, you were wrong. It was indeed from the planetary science decadal. And so this is a hand being reached out from the planetary science decadal, saying, hey, there needs to be more crosstalk between our divisions. And indeed, that's true. But notice that they're talking about in a mission context as well, which is going to be increasingly important over the coming decade. And I'll speak to what some of those missions are. Now, particularly when I'm talking to an astrophysics community, I always like to show them this summary table of the major questions that were being raised in the planetary science decadal. And you can see that there's a series of 12 questions, and they're categorized under themes. And they're covering all different parts, interior processes, atmospheres, and so on, of planets. And then we get down to the bottom and we see Q12, which is exoplanets, which can make it seem like an afterthought. But nothing could be further from the truth, because it's all themes. In other words, the reason that they put it there is because exoplanets really does connect to all the major questions that the planetary science community are thinking about. You know, when I talk to the exoplanet community about this crosstalk between divisions, one of the major pushbacks I get from my exoplanet colleagues, which, as I mentioned, are mostly stellar astronomers. And what they say is, well, you know, all of that planetary science stuff is cool, but I just don't see how it connects to observables. But the answer to that is that it really connects everywhere. Because, for example, if you're a person who's interested in planetary architectures and demographics of planetary systems, then that connects to how planets form and how they interact with their disks, which is in the origins theme. If you're a person who's interested in bulk densities of exoplanets, as many people in the exoplanet community are, then masses and radii, and that, of course, is built from the bottom up rather than a top-down approach, which is, what are the interiors of planets and how are they changing through time? Same thing with atmospheres. Of course, we're in the era of JWST, and atmospheric characterization is only going to increase as time moves forward. And the atmosphere didn't get there by itself, in the sense that it's a process of degassing. And so that connects to the planetary interiors as well. And so, as I said, the connections really are everywhere. And once again, this is a hand being reached out from the planetary science community to the exoplanet community, saying, really, we want to talk to you about every individual component of what we care about and what the fundamental science questions are that we're trying to answer in planetary science. So, to give just a few takeaway points from this, first of all, one of the sobering points: we're never going to have in situ data for an exoplanet. Now, sometimes when I say that, I'll hear somebody at the back say, well, not with that attitude. The nearest exoplanet, by definition, is Proxima Centauri b. And I don't think we're sending a lander there. I don't think we're sending an orbiter there. I don't think we're even sending a flyby there. Not in my lifetime. And so that means that everything that we're doing with exoplanets are inferences, a lot of the time based on models, and those models originate from the in situ data, which we do have, which are from right here. So that's why that is so important, because when we look at the uncertainties, and there are many, with planetary science and solar system work, then those can translate catastrophically into our inferences from the exoplanet observations. And so we've got to get that right. Otherwise, we'll be wrong for something that we can't even check. And so that's one of the really key points that has kept me up at night for a long time. And so there's a variety of ways in which we can address that, and I'll be talking through some of that today in these mission concepts and things that we can do with this. But it's really important to recognize that although the quote that I showed you at the end was the planetary science decadal saying, hey, we need to have representation. Actually, when you look at the wording of both of these reports, they both advocate for that. They both advocate for having this representation on both sides. So I wouldn't want to give the mistaken impression that this is a one-sided reaching out. It certainly is not. So now, by way of example, what I would like to do is talk about my favorite planet. And of course, I am talking about Venus. And Venus has been a fascinating case study in why this is so important, why this topic is so important. Because, as I mentioned, I was originally starting out doing a PhD on Venus. And then I switched to exoplanets, and now I've kind of gone back into this weird hybrid world, but I'm largely working on Venus. And the interesting thing about that is when I joined the Venus community about 12 years ago, it was a fascinating time of seeing the Venus community at a period when they hadn't had new NASA data, the Magellan data, for almost 20 years. And it was somewhat of a disheartened community. But there is a lot of things which have changed recently. And you would have seen that. Fortunately, the selection of missions, which I'll talk more about, which has injected a lot of enthusiasm. But there's a reason why those missions were selected. And that's because of the realization of the outstanding questions of Venus and how that applies to exoplanets. Now, one of the interesting things about Venus is that it was one of these objects that was thought to be, at least from people outside of the Venus community, to be a solved problem. It's in a post-runaway greenhouse state. It's closer to the sun. Can we go back to Mars now? But more recent work on this has shown that it's far more complicated. Now, don't get me wrong, there's been a lot of papers over numerous decades that have spoken about the potential past wet history of Venus. But the fact that it's closer to the sun, receives twice the amount of solar energy, is only part of the issue, because there's a lot more differences between Earth and Venus than just that. For example, rotates very, very slowly, and almost vertical rotational axis. Little to no surface subduction. Outstanding question there, which is very, very important for the geologic history of the surface and potential past temperate conditions. Negligible magnetic field, which is related to the state of the interior, which we know almost nothing about, and the fact that it doesn't have a substantial moon doesn't really help with that, because it means it's very difficult to measure, for example, its moment of inertia. But one of the advances which came along is the development of 3D climate models. Because the 3D climate models, prior to the 1D climate models, which are just calculating the energy budget from the surface to the top of the atmosphere, when you start adding in the 3D component and looking at the spatial nature of the energy budget, but also the effect of rotation, shows that it's far more complicated than that, such as having clouds forming at the substellar point, which can actually keep the surface cool up until about a gig year ago. And there's work of Mike Way, who's one of my collaborators on this, who's done a lot of work on that, along with many others. And so it really brought a lot of this, these questions back, saying, wait a minute, we thought we'd figure this out. we are far from figuring this out because it's a very complicated parameter space to try and explore. So one of the ways in which I see this issue, the differences between Earth and Venus, is ranking all the factors that you know about the planet, how they're the same, how they're different, and then trying to understand what I refer to as the first order, second order, third order effects on terrestrial planet evolution through time. Some of them will be important, some of them will be incredibly important, some of them may be things that are important but are dependent on other parameters. So understanding what are the first order effects on terrestrial planet evolution, that's the important thing for applying to exoplanets, particularly as for exoplanets, many of the things that we can measure for Venus, we can't yet measure easily for exoplanets, such as the rotation rate, which I put it to you is actually a first order effect on terrestrial planet evolution. So it's an important thing to understand, particularly as sometimes I remember the first exoplanets in our backyard meeting, and I gave the very first talk at that meeting summarizing what we know and what we don't know about the terrestrial planets of our solar system, and I stepped through Mercury, Venus, Earth, and Mars. And two interesting things came out of that. One was that when I showed the picture of Venus, I kind of cheekily showed this picture, and people say, wait a minute, that's not Venus. And I said, is it not? It's the axis of time. You need to think, in the fourth dimension. How have these planets changed with time? How has Earth changed with time? And that was the other interesting that came out, because when I spoke to an exoplanet person at the first break after that talk, they said, oh, I noticed you spoke about the outstanding questions regarding Earth. I never really think of Earth as a planet, which is part of the problem. So, we need to be thinking about how these planets are evolving through time, because obviously when we look at an exoplanet, we're seeing it at a certain stage of its evolution. Say, for example, the TRAPPIST planets, which are around about 8 gigayears old-ish, so about twice the age of the planets of our solar system, and that almost certainly matters in terms of where they are in their evolutionary state. So how do we solve this? Well, this is where the collaboration effort comes in, because the way in which I try to approach this for Venus and for all the planets of our solar system is a two-pronged approach. On the one hand, we have a planet within our solar system, which we have in situ data, or at least high-resolution data that we don't have accessible for an exoplanet. And so in the case of Venus, we can start to study what the evolutionary history of Venus is. But then on the other hand, we've got exoplanets, and what I sometimes refer to as exoplanets as, I call it the statistical hammer. Because what exoplanets really brings is numbers, vast numbers. And you'll hear a lot of people refer to exoplanets as putting our solar system in context, which is a great phrase, but what it's really referring to is just the bulk of the numbers that exoplanets bring. And then we can start to answer these questions about whether the solar system is normal or freakishly weird, and all these sorts of interesting demographics and context problems. So for the evolutionary, or rather, sorry, for the exoplanet approach, this is where we can start to see what the exoplanet data is showing us. And like I said, I went to the Kepler folks and said, well, what you really have on your hands here, potentially, is a lot of Venus analogs, because remember, the Kepler mission uses the transit method. The transit method is overwhelmingly biased towards short-period planets, and if you're interested in Earth-sized planets or Venus-sized planets, then you can start to think about what that demographics is closer to their stars more easily than those planets which are further out in the habitable zone. And that's when I was writing papers about Venus analogs from Kepler and started writing about this concept called the Venus zone. Now, the Venus zone is just simply, it serves to say it's a similar purpose as the habitable zone, which is not to tell us if the planet is habitable. It doesn't tell us that. It's to give us a target selection tool where we can start looking. And so the habitable zone, which is shown over here on the right, has an inner boundary, and that inner boundary has a rough area which in the original Jim Casting and Ravi Kopparapu papers is referred to as a runaway greenhouse boundary, where essentially you're transporting a lot of your surface water into the stratosphere and saturating the stratosphere. And so we use that as the outer boundary for the Venus zone. And then the inner boundary, which is in a constant state of, if you'll pardon the pun, flux, because we're trying to figure out what that actually means. And this is where there's a lot of expertise in this room, because what that's really is talking about is atmospheric loss. That atmospheric loss boundary at the inner edge, which in the original paper, we were estimating that from this concept of the cosmic shoreline, which Kevin Zanley and David Catling have written a lot about, just based empirically of looking at the objects in our solar system based on surface gravity and insolation flux, which have atmospheres and which don't. So we originally used that, but using these rough boundaries, what we found is that for having a terrestrial planet within the Venus zone, you get about half of the G and K stars from Kepler have that, which is pretty cool, because it means there's a lot of potentially Venus-like planets out there, keeping in mind the caveat I mentioned earlier, that there are a lot of other differences between Venus and Earth, and also this axis of time. But this is one approach to understanding if indeed what we thought all along was true, which is that incident stellar flux at the top of the planetary atmosphere is overwhelmingly the first order effect, and that a lot of these other parameters ended up being secondary effects. Because if you are able to retrieve atmospheres of planets which are in the Venus zone, and it turns out that they're all in a post-runaway greenhouse state. That would be really interesting to know. But, like I said, there's the axis of time, and if you were to look at the ages of all these planets and find that they're all between 8 and 10 gigayears, then that's a different conclusion again, because all you might be saying then is that, well, all planets turn into Venus eventually. Some people say that, that Venus is kind of a preview into Earth's future, that sort of thing. So this is a pathway to do that. Now, the Kepler targets, of course, were fairly faint, and so not easy to do this kind of work to follow up with spectroscopy, transmission spectroscopy, to get first-order atmospheric compositions. And so then we turn to TESS. And so TESS, as many of you know, is the current Transiting Planets mission, which is deliberately all sky and focused on bright stars, which can then be synergistic with JWST observations. So this presents us the opportunity to produce a catalog of exovenus candidates and rank them in terms of whether they are good targets of JWST. Now, JWST, and I'll be talking a little bit more about the role of JWST in this and its mission lifetime. It does have a limited lifetime, but I would say that we do need more targets, because there's only a certain amount of bright stars in the sky, and so not all of these candidates are created equally. But this is from a catalog that my graduate student, Colby Osberg, produced, and he has published extensively on this topic. He's defending his job hunting, just want to throw that out there, but he found hundreds of candidates that met this criteria just from the current test inventory. So that's really great. It means that we could have a lot of opportunities to start build up as a statistical sense of this. Now, of course, this takes time. JWST, despite my best efforts to convince the TAC otherwise, is not a Venus mission. But we are getting data on some of these nonetheless. Now, in the meantime, what we have also been doing is running climate simulations for many of these. And as I mentioned, the 3D climate models has really changed the narrative of a lot of this discussion about Venus and Venus's past, because it does show that you can have these past temperate periods. And I mentioned the work of Mike Way, but there's a lot of other people who have been thinking about this. And so through all of these candidates that we're producing, we're running 3D climate models and trying to produce outcomes that have some predictive capability. And what comes out of that is modeled transmission spectra. And so that's what's shown on the right, once again from Colby's work. And the interesting thing about that is when it comes to transmission spectra, you have to remember that you're essentially sampling the top of the atmosphere. And the top of the atmosphere is only part of the story. Or at least if you were to sample, say, the top of Earth's atmosphere and the top of Venus's atmosphere, how easily would you tell the two apart? Because from that, you have to infer, say, a pressure, temperature, chemistry, compositional profile that goes all the way down to the surface, because ultimately what you're trying to do is infer surface conditions, usually. But that's difficult because it becomes very degenerate. And so, for example, when you look at the differences between Earth and Venus, you actually find that they both have, at that altitude, very strong CO2 absorption. And so it can actually be very, very difficult to tell the two apart, particularly at JWST passbands. You'd be looking for things like the 4.3 micron absorption features and others. But this is work that we've been thinking about a lot about, well, what do we need to do in order to go further? And then that's when we start talking about future missions. But just to give you a bit of a summary of some of the issues with categorizing Venus exoplanet candidates, as I mentioned, one of the conclusions earlier on that we found is that fortunately there's a lot of these candidates out there, so there's a lot of work that we can do. Something that I mentioned in point 2 that I'm not going into any details in this talk, but I'm happy to talk about this further with any of you, which is a fascinating thing about Venus, which I think is underappreciated, particularly given the focus of it in exoplanet science, is tidally locked planets, because often we're talking about planets which are close to their stars and are assumed to be tidally locked, and maybe they are. But Venus is almost tidally locked. And an interesting question to ask is, why isn't Venus tidally locked? And he could say, well, maybe it hasn't had enough time to do it yet, but actually it has. And if you do a rough calculation from Venus's present state, how long would it take to be tidally locked? It's about 5 million years. So it's not actually all that long. Why isn't it? And it goes hand in hand with the fact that it has an extremely thick atmosphere, which is super rotating. And so there's a huge amount of dynamical energy which is being transferred between the solar body and the planet and the atmosphere of Venus, which is incredibly fascinating and something to think about for the cases of exoplanets where we assume that they're tidally locked. But in terms of where we are going next, there's a lot of opportunities which we're taking advantage of now. I've mentioned JWST. And as I spoke about, there's quite a few bright targets, but not nearly as many as we would like. More will be coming. Tests will keep going, and there are other missions coming up, which I'll talk about in a moment, that will provide more of these. But as I mentioned, the CO2 absorption features at 2.7, 4.3 microns do tend to be a little bit degenerate if your real focus is to say, hey, this is a Venus, hey, this is an Earth. And so that's an issue. And so the midterm opportunities, which I'll be talking about more in a moment, is because part of the reason that it is so degenerate is because we know so little about the middle and deep atmosphere of Venus. And so getting those PT profiles right, because when Zach and I were talking earlier, he says, I keep seeing different PT profiles for Venus. What's going on? Some with a thermal inversion, some without it. And so obviously we need to fix this if we're going to be able to be applying the nearest Earth-sized planet to exoplanet observations. Long-term opportunities, this is where it really starts to solve the issue with transmission spectra, because then you're moving into the era of emission spectra. And once you're moving into emission, then you can tell a lot more about the planet. If you're fortunate, maybe you can even extract the rotation rate. But really, it's about moving into different pass bands, something like UV, which will be indicative maybe of ozone, and ozone is actually something which helps to break the degeneracy between an Earth analog and a Venus analog. So I'm just going to spend a few moments before I talk more about the missions more generally and what the collaborative opportunities are, talk about the Venus missions, because it was the highlight in a dismal period of the pandemic. It was June of 2021. And as many of you know, there were four New Frontiers missions up for grabs. And there was a televised whole thing with the NASA administrator and a very surreal interview with William Shatner. And it was a lot of just keeping us guessing. And Twitter was going absolutely crazy trying to guess which out of the four would be selected. They were going to select 2 out of 4. 2 were Venus, Veritas and Da Vinci, and the other 2, of course, Trident, which is a fantastic mission, and the other one being the Io Volcano mission, also great. Like it must have been a very, very difficult choice. But myself and the others in the Venus community were thinking we've got a 50% chance of getting one. And then finally, after William Shatner went away, we heard the answer, which was that we got both. And myself and my Venus colleagues, I think it's safe to say that we didn't feel bad about that. We felt that we were owed. And it's fantastic also because both of those missions are very synergistic with each other, because Da Vinci, which I'm on the science team for, that is an atmospheric probe, which is going to finally provide incredible data of the pressure temperature profile, essentially from the haze layer, where it's going to release the parachute and free fall down to the surface in a 45-minute descent profile, which will provide the pressure temperature compositional chemistry data for Venus far better than ever before. And Veritas. Veritas radar mapping, it's Magellan++, but it's even better than that, because as I mentioned, one of the outstanding questions is little or to no subduction on the surface of Venus? Really? Is that true? I mean, probably not. I mean, we now know, just over the past year or two, that that Venus is pretty volcanically active, something that we had inferred from the SO2 in the middle of haze layers. Like, yeah, that sulfur's coming from somewhere. But having that direct confirmation is pretty incredible. And so there's obviously a lot to learn about the geological landscape and activity that's still going on Venus today. So that was pretty incredible, but of course it didn't stop there, because not long after the Europeans announced that they were going to deploy Envision. And the Envision mission is pretty incredible. It also does be doing a lot of the radar work that Veritas does. In fact, there's a strong overlap in the hardware, but it's going to be doing a lot of different things about the surface compositions that Veritas won't. And in particular, it's going to be looking at the difference between, say, basaltic and granitic compositions, which may be indicative of past ocean floors, if indeed there were that period in Venus's history. And one of the things to mention about those is a lot of conspiracy theories came up, you know, when this happened. It's like, well, you know, phosphine was announced the previous year, is that way? And is Europe just following the Americans? No, none of that is true, because these missions, these selections take a long time. And that process was started before any of that happened. And particularly for ESA, trying to get the you think it's difficult with the election cycle getting the states here to agree on who's going to lead us. In ESA, it's also difficult to get the individual member states within a mission to move in one direction, and that takes time. And so this was a long, well thought out process. And I think it's turned into a fantastic opportunity coming in the next decade. So now with my remaining minutes, I want to talk about the coming planetary missions and what the synergistic opportunities are. Many of you have seen this. I saw it in the department hallway, actually. It seems like it's changing minute to minute. Every time I go to the NASA headquarters, they have an updated version. But you can see that there's the astrophysics mission is shown in the top left, or a subset of them. And we have a lot of Earth science missions, which are also extremely relevant for exoplanetary science. We've got color codes, depending on the status of the mission and whether there's ESA involvement in those missions. Of course, we have heliophysics represented on here as well, and heliophysics is a crucially important part of this whole story. You may see that I have kind of hand-drawn in Uranus flagship. I added that because I'm actually very excited about the top-ranked recommendation from the Planetary Indicator, which was, hey, we need to go back to the ice giants. Because I remember, as Shannon mentioned, I grew up in outback Australia, and I watched the TV in 1986 as the images came in from JPL. Very, very exciting. Little did I know back then that that would be the only data that we would have. We flew past Uranus just long enough to say, wow, that magnetic field's weird. We should come back and check that out, and never did. So we need to go back. But I want to speak now to some of these planetary missions and the timeline and how that overlaps with the astrophysics missions. But buyer beware, right? Because these dates are always changing, as those of you in the planetary and astrophysics communities know. And often when you go to the NASA website, before each time I give this talk, I go check the dates. And it always says no earlier than, right? So keep that in mind. But these dates are placeholders. So let's take a look at some of the missions that we're thinking about on our timeline. Here we are in present day. And I've got the planetary science mission timeline shown on the top, astrophysics on the bottom. And the planetary mission timeline, apologies in advance if I don't highlight your favorite mission here. Believe me, it was like a space. But just some of the ones that I've highlighted there. Juno, we've all seen the incredible images of Juno, but more particularly, it's really about understanding the interior composition of Jupiter. Turns out there are many, many open questions about that. And that is, of course, the overwhelming dominant planetary mass within our solar system that we still have fundamental questions about. And so Juno is extremely important for that. MAVEN, you are all very familiar with. Atmospheric loss is such an incredibly important topic within exoplanetary science. And so MAVEN is, I would say, the major contributor to that science. JUICE, which has successfully launched and on its way to the Galilean moons. And you'll notice that I have a date here for orbital insertion. It's highlighted in yellow. I'll come back to that in a moment. And I think the next decade is going to be a real high time for asteroid science, which is so important for the formation of the solar system and the disbursement of volatiles within the solar system. Critically important for that. And so we've seen the important results from DART, OSIRIS-REx, and Psyche and Lucy have now successfully launched. In the meantime, over here in the present day, we have Gaia, which was launched in 2013 and rapidly approaching, I hope, the 4th data release. We've got TESS, launched in 2018, and of course, is Kevin here? Oh, put cute on just for Kevin. That's really important though, because I think we're entering an incredible era of CubeSats. There's various reasons for that. One, of course, is budget. But the other is because that capability is growing dramatically. And I think having proof of concept missions like CUTE is so important for that. And of course, JWST. I'll come back to this mission lifetime. I said could last 20 plus years, as many of you know. By the way, how many people got up Christmas morning and watched the launch? I think it was it 4 a.m. California time, which 5 a.m. here. But yeah, I just stayed up all night Christmas Eve and played video games because I knew it would be easier to do that than wake up in time for it. But that was an incredibly successful launch. They conserved a lot of fuel, which extended the mission lifetime. And that's going to be incredibly important later on. So right on our doorstep, Europa Clipper. And that's going to be launched, or at least the launch window opens on October 10th. You also, I'm sure, know that there was a hurricane sitting on the Gulf. We'll see how that goes. But hopefully we're able to get that launched and on its way. And of course, that's going to be an incredibly important mission for icy moons and determining what the water inventory is and what that means for planetary habitability. And on the astrophysics timeline, not long after that, we're going to have the Pandora mission and the Plato mission and the Roman mission. Pandora is going to be studying stellar activity, and so that ties back into the atmospheric loss processes for exoplanets. We will have the Plato mission, which is a European mission, and that is going to be tests on an even larger scale, which is incredible. And once again, focusing on the bright stars, which will provide even more JWST targets. So that's going to be really important. Roman is launching soon, and that's going to be doing a combination when it comes to exoplanets of things like microlensing discovery of exoplanets. Scott Gowdy talks about this a lot. And so there's going to be a huge, in terms of demographics, what I mentioned about statistical hammer and numbers, that's going to be a huge number of planets. And it's also going to be doing direct imaging as a technology demonstration, which is going to be awesome. Back to Planetary. Now, Mars sample return, as many of you know, is a difficult conversation at the moment. It's had cost overruns. It has triggered the attention of Congress, which you never want, usually. And the original plan was 2028 launch and return in 2025. Now the revised plan is 2033 launch. 2040, although the current reaching out to industry partners, my understanding is to try and bring that back because 2040 starts to become difficult. But we'll have Dragonfly launching in 2028 and then deployment in 2034. Then Ariel, European mission, again, and that's going to be launching in 2029, and Ariel is going to be a mission which is focused exclusively to essentially transmission spectroscopy of exoplanets. So it's going to greatly increase the inventory that we have of compositions of exoplanets, mostly in the sub-Neptune, like kind of mini-Neptune regime, but it's going to be important nonetheless. And Uranus Orbiter and Probe. This is also a difficult conversation because, as I mentioned, that was ranked top in the planetary science decadal. But in order to get to that launch window in the early 2030s, which it really needs, that's part of the reason why it was ranked so high in the decadal, because of the low risk involved. It needs those gravity assists in order to get orbital insertion in the early 2040s. And that is rapidly approaching. So that's becoming difficult to determine whether we can send a flagship back to Uranus in that timescale. We'll see. We might need to revisit that in the next decadal. Now, then we enter this era of Venus, and that's going to be fabulous. We're going to have Da Vinci, Veritas, and Vision all around about the same time. The Envision launch date might be a little bit later than that. But at the same time, I've mentioned that this is going to coincide with about the halfway point for JWST mission lifetime. And then after that, we start looking into the far future. And that's when we're talking about directly imaging an Earth-sized planet around another star. And there's both NASA and European efforts in that regard. Habitable Worlds Observatory, the LIFE mission. But this is, we're looking towards the 2040s. Now, a couple things to point out about this. Whereas with the astrophysics missions, you launch a mission, you usually go through a calibration phase, and then you start collecting data, right? Instant gratification. Your planetary mission, you launch your mission, and then you go away and play World of Warcraft for 5 years or 10 years, and then you come back and you get science maturation. And the interesting thing is that, according to the current schedule at least, a lot of these missions are going to achieve science maturation in the early 2030s. And that's close. It may not feel close, but let me tell you something. 6 years ago, Zach and I were at Cape Canaveral, and we were both cheering the launch of TESS, and it was fantastic. That event took place as far as in our past as 2030 is in our future. So these data are coming, and they're going to be transformative, not just for planetary science, but for the way in which we think about exoplanets. And so the time, I would argue, to get involved in these missions is right now. And so when it comes to things like the Venus missions and being halfway through the JWST mission lifetime, it means that there'll be plenty of time left within JWST operations in order to incorporate that data into the JWST science. We'll be able to use those lessons learned then for about another 10 or so years of transmission spectroscopy of exoplanets. So that's great timing. The Uranus orbiter and probe, fingers crossed that we can actually meet that launch window. It means that you'll have orbital insertion around about the time that we'll be directly imaging planets around other stars, which, as I said, the focus is on, or always on, Earth-sized planets. But it's really about planets in general in the habitable zone. And this is for the ice giants, which is a significant amount of the known exoplanet population. So figuring this out for the ice giants is going to be critical for understanding the science that will be coming from that exoplanet population. So just as these are a couple of the points that I've made already, such as the synergy with the Venus mission, how that ties into JWST, the synergy with the Uranus orbiter and probe. If that mission is indeed moving along, that's going to be incredibly important. But things like the icy moon missions, Europa Clipper, Dragonfly, etc., that's going to be fundamentally important for thinking about icy worlds on a much broader context, and about the volatile inventory of different kinds of exoplanets and all of the discussions that we have about astrobiology in habitable worlds. And so the connections, as I mentioned, are really everywhere. If you look at what are the science questions of these planetary science missions, what are the science questions of the astrophysics missions? I know it sounds like I've been mostly speaking to the exoplanet community, but it's really both sides. As I said, both decadals advocate for this. And so I want to just leave with a few pieces of advice, because one of the difficult things was, where do you even start? And of course, that's one of the purposes of the exoplanets in our backyard meetings, to have equal representation from both communities. So you really do force people into a situation where they're talking to people outside of their area of expertise. But when it comes to thinking about this in general, the piece of advice that I have are examining the planetary science and the astrophysics literature. Now, this is a tough one, because it's hard enough to keep up with like the archive postings in your own field. It really is. So the invitation from me to say, hey, why don't you double your workload? It just sounds bad. But just to be aware that there are significant advances happening in the other field which are directly applicable to yours. And finding the people who can really report on what the takeaway points are is really important, and having those contexts in other areas that you can easily reach out to. Now, how do you make those contacts? This is where you just got to go to meetings. I mentioned 12 years ago that I got back involved in the Venus community. What that looked like was essentially me going online, finding that there was a thing called VexAg, and a guy named Bob Grimm, many of you may know Bob, he was the chair of VexAg at the time, and I sent him an email and say, hello, Bob, you don't know me, but do you mind if I come to a Venus meeting? And I was like, yeah, sure, of course. So I did, and I went there not knowing anyone. And it's been just an incredible journey ever since, meeting people, having those connections with the science. And so there are many opportunities for that. The Outer Planets Analysis Group, VEXAG, there's one for each of the bodies in our solar system, and also, of course, ExoPag, if you're interested in going the other direction. So exoplanets in our backyard. The next one is in Louisville, Kentucky, coming up in November. Really great series of meetings. I also suggest reaching out to the mission scientists, because believe you me, they really want to hear about the relevance of their missions. Nothing would make their day more than somebody reaching out saying, I don't know if you've thought of this, but here's a value-added piece of your mission. They love it. And I really encourage you to do that if you've looked through their mission material and say, you know what, I can work with this. And particularly for the early career folks here, I highly recommend the mission design schools. And so there's the astrophysics one, planetary science, heliophysics. I actually got an email right before this talk for the AMDS. These are normally held at JPL, and everybody I've spoken to have found those incredible. Working with a bunch of other people that you've never met before on creating a mission from the ground up. So I know I'm pretty much out of time, so I'll just finish with a couple of main thoughts. What I'll just focus on these last couple here, and just re-emphasize that both decadals are advocating representation from both sides. I think this will become even stronger in the next decadal. It's hard to believe that we're in the mid-decadal era already. And the heliophysics decadal, which hasn't come out yet, but my understanding is that that will have similar advocacy for this cross-disciplinary talk. Their work certainly is very, very important, and I think that will be great to have that added to this as well. But as I say here in this final point, it's really fundamental combination. Solar system data, what I call the statistical hammer of exoplanets. It's crucial to playing our solar system in context and really making that phrase mean something real, that we can see what those connections are. And understanding the evolution of exoplanets. So thank you. I hope I've given you something to think about today, think about opportunities that might exist. Happy to talk about more of the itty-gritty details of things that I've mentioned today. Thank you very much.
Okay, do we have questions for Dr. Kane?
So early on you mentioned rotation rate being like a really fundamental thing for planet climate. And you showed this map of a like simulated surface temperature of a pretend world, which I know we don't have continents on exoplanets. Well, they have continents, but we don't know what they look like. And so I was just curious about your thoughts on how we could get at rotation rate. Is it all like reflection features in the optical of continents and oceans and trees rotating in and out of view? Or can we see things in thermal IR from surface temperature maps like this as well?
Yeah, this is a scary one for me, because as I said, I'm increasingly convinced that it's a first order effect, and it's when we are running the climate models, we have to just try a few scenarios and see how it matters, and it matters a lot. That's why I say it's a first order effect. In terms of how we measure that, there's a few things to think about. One is that I've worked with the EPIC camera data on the Discover satellite to observe the Earth as an exoplanet and convolve those data to a single pixel. And I can recover Earth's rotation rate, but we can see the surface, and it's a rapid rotator. For an exoplanet, realistically, it's going to be very low cadence data, potentially haze cloud covered. And in the case of Venus, for example, because the rotation rate of Venus's atmosphere is about 4 days because it's super rotating. And so if you're inferring from an atmospheric rotation, you may get that catastrophically wrong. And so, so there are several ways to get around that. Hopefully, we'll have cases where you have enough transparency of the cloud layer where you can extract those data from the rotation of the planet. But like I mentioned, it depends on what cadence that you're getting during a planetary orbit, and that's going to be tough. Or you can make that transparency happen at different wavelengths. And this is where we can learn a lot from Venus, because there's been several ground-based observations, but things like the Parker Solar Probe, which is being able to see through the clouds of Venus. And so that's where I think we need to understand things like the transparency of Venus's atmosphere as a function of wavelength to really be able to solve that problem going forward.
Hey, I'm Travis Metcalf.
Hey, Travis.
I wonder if you could just say a few more words about this stellar activity mission that you mentioned, Pandora, and also about the stellar characterization that's built into the Plato mission.
Oh, good questions. Well, I'll just speak to it. But Pandora, I don't know a lot about the Pandora mission, except that it's what class of mission is it? The PI is Lisa Quintana, and apparently this is going forward very well. But my understanding is that it's mostly X-ray. What I don't remember is how many targets it's going to be able to observe during its mission lifetime, which I think is a really important aspect of these smaller telescopes, which are generally just sitting on one target. So that's something that I need to check out. In terms of Plato, Plato's going to be really interesting because it's going to be observing a vast area of the sky. As you know, Travis, with tests, it's like these 30-day windows, whereas Plato is a lot longer. And so my understanding is that the astroseismology community are extremely excited about Plato, since it will give them much longer time series than they've been getting with tests. And so my understanding is that the astroseismology component will be a very, very important part of that. Ward actually may know a lot more than I do about that.
My question is actually about another area of exoplanet science that I wonder we might be able to learn quite a bit from the planetary science community, and that is rocky exomoons. And I was wondering if you could potentially speak, especially in the 2040s, once we have the ability to better understand these sorts of systems with habitable worlds, what might we be able to do with synergies between planetary science and exoplanet science related to rocky exomoons?
Yeah, exomoons is an interesting one because we know we're out there, we just haven't hit that sensitivity limit robustly, except for the really weird, oddball cases. And so, as you may know, there's a huge effort going on within the HWO community at the moment to develop science cases. I'm not actually sure if anybody's developing the exomoon science case. I haven't spoken with David Kipping recently to see if he's still ringing that bell. But I'll be surprised if that case isn't in there. But it may be a case of science that you get for free. Because meaning, the reason I say that is because there are science cases being developed for looking at giant planets. And even giant planets beyond the snow line. You have a wider separation, but there's less flux, so there's going to be a limitation there. But that's where you might necessarily expect to find the exomoon population. So I'd hope it will come out of that component.
Why don't we start with
Just a general question. You talked a lot about the synergy between solar system objects, Venus specifically, and exoplanets. But what do you think is needed? You talked about a lot of missions that are coming, and maybe in some sense we just wait 15 years and then we have all the information we need. That's tongue-in-cheek. Do we need NASA to restructure itself in some way? Do we need more people to be willing to cross traditional boundaries? Do we need scientists who are trained from the beginning to cross these boundaries? What do you think the barriers are? What do we need?
That's a really great question, because I know that this has been a challenge and continues to be a challenge for headquarters, because they have these 4 divisions which are relatively walled off when it comes to funding models, at least. Although they're an enormous advocate for having cross-disciplinary talk, it's difficult for them to implement it in practice, is my understanding, because of these barriers. And as you know, like one of the cases, this is ICAR, which is in astrobiology, which is in astrophysics. So I think it does need more people from early as possible getting involved in this cross-disciplinary talk. I think that's how the change happens from the ground up. And that's why we're having these cross-disciplinary meetings, and obviously other ones like AbSciCon, where we're having people exposed to these different science cases. Because this is, at the moment, my understanding, still continues to be a problem. For example, NASA assembling a panel that can properly assess a specifically cross-disciplinary proposal. That is still challenging. But yeah, I think it needs to, it's a growing change in our culture for the good.
Let's thank our speaker again.